Again, Zach?
Action.
Thank you. Okay, square root of a function is what we're doing next. We've already looked at just the radical functions. Same thing here, except now our functions are only square roots. They're limited to square roots. We're not considering cubed roots or anything for this course. But here's where we're going to start. We're going to say consider the functions, and we're making pretty simple ones here. Y equals 2x plus 4. So that's a grade 10 type of function. What kind of function is it? It's linear. All right, so our friend in the front here, Jake, is reminding us that this is a linear function. All taking the square root of a function is, wait for it. Are you ready? Here it is. Y equals 2x plus 4 square rooted. Wow, that's some tough stuff. So this is the square root of the original function. Now, Zach is asking, why would you do that? Now, really, there is no purpose for doing that. What we're learning here, you got to remember, this course is just building on stuff you'll use if you go beyond the course. That's the goal of every course you take in high school. If you want to reach the next level and have some background knowledge, the information that happens and the characteristics that happen when we square root a function is the important thing. The reasons for square rooting it are few and far between. Jake?
So what happens if it's like 2x squared plus 4, and then would you
No.
square the entire thing?
You'd square root the entire thing. So Jake's asking if it was 2x squared minus 4, you said, or it doesn't matter. You'd still square root it all and just leave it, and we'll go from there. Okay, so now when we're looking at these two functions, we're going to graph them both. Okay, so the first thing we're going to say here is create a table of values for both functions. And then eventually here, we're going to graph it. So we're going to see the characteristics. So the characteristics that we're looking for here, the skill, is that we know how to graph just a normal function. But now if we take that, any function we've ever graphed before, and take the square root of it, what happens to it? So that's our goal. Not really why we do it, just what happens when that goes on. Okay, so let's create the table of values. First column, we're going to choose some values of x, but I'll give you the values of x because we learned last time that it's nice to choose values of x that work out nicely. Okay, so the original function, y equals 2x plus 4. And then we're going to look at y equals that. Now, what did I write in that last column? What is this last column right here saying, basically? The square root of the function before. So we could have wrote y equals the square root of 2x plus 4, but just to show you how they can write this a little differently, we're going to choose these values for x, -4, -3, -2, 0, and 6. Now I'm going to give you a minute or 2 minutes to go through and create the table of values for, first, the original function, and then for the square root function, and we'll talk about them. Okay, so put those x's in for all the x's in the functions, and let's get those values to talk. This first column, we just had to plug these x's into this y equals 2x plus 4, and we get these values of y, -4, -2, 0, 4, and 16, which tells us that this creates ordered pairs at -4, -4, -3, -2, so we can graph these guys, 0, 0. Oh, I'm getting mixed up here. Did I miss a number? Oh, right here, -2, 0, right? That's my bad. -2, 0, and then 0, 4, 6, 16. So this is the original function. Now, if you even look at the notation here in the last column, it's saying y is the square root of the original function, f of x. In grade 10, you learned function notation. We reviewed it in grade 11 and in grade 12. F of x is a fancy way of saying y. So all we have to do to get these points is to square root the y coordinate of this original function. We just have to square root all of these. So how do you square root a -4 in the first one? You can't, so that leads to a point that is undefined. And then I'm trying to square root of -2 in the next one. It is undefined. Now, if I square root the next guy, what do I get? 0, which would lead me to a point that's -2, 0. Transformations, you should know what the name of this point is. Here it is on the square root, -2, 0. The original is -2, 0. Did that point move? No, so what's that called? It's an invariant point. That point did not become affected by this. The next guy is going to be a 2, which gets me to 0, 2. And the last guy, whoops, is a 4, so it's going to be 6, 4. So now we have some points to plot for both functions. We can see now, here we got some undefined stuff going on. This means that there's no point on this graph that's going to be the radical of it. It's just going to start out of the blue somewhere. And we talked about radical functions in the last lesson, how they just sort of started and then started arcing off. This is what's going on here. So let's graph these two guys. Just create yourself a scale, and you can see you need to go up to 16 on one of them. Okay? Two, 4, and 6. And then 2, 4, 6, 8, 10, 12, 14, and 16. I think 16 was our largest one, right? So if we were to graph the first one, it was just a linear function, we said. How many points do you need to draw any linear function? 2. To draw a straight line, you only need to graph 2 of those points in the first column. So I'm going to pick 0, 4. That's an easy one. And what else? 6, 16. So someone way up here. Jake said it. He needs to take credit. And then connect them, which you could probably do better than I can. Oh, missed it. Totally. Does that go on forever both ways? Sure does. It's just a snapshot of this little thing. Okay. So now if we look at the last column, and we're going to graph the radical function.
Put on the same graph, please.
Yeah, we'll put them on the same graph for sure. The first point that we have is -2, 0. So back here, -2 is going to be -2, 0, somewhere right about there. And then
0 and 2.
0 and 2. And the last guy,
6 and 4.
6 and 4. Now, I want to show you guys something that you're going to have to get used to drawing. This graph is actually going to do something. Crap, and I missed that entirely. Let's back that up. It's going to be hard to draw it on this scale. Whoa. I'm going to just change my points to show, even though it's not going to be to scale. The graph here, we missed our points, but this radical graph, there is always going to be this little section, and we're going to look at it in depth more. It's always going to be this little section where it bumps over the original graph. This little window where the radical function actually takes values that are higher, then it gets underneath. So these are how these two functions compare. Now, Alec already pointed out that the linear graph, the original one, extends indefinitely in both directions, but the radical graph is just starting somewhere. Okay, and in this case, it just started at -2, 0, and it takes off. Why will this graph not be underneath unless there's transformations involved? Why would it not be underneath the x-axis? Right, no square roots of negatives. Okay, so the next example, let's order on, and I'm going to ask you guys to see if you can sketch it the same sort of way we did before. That came out of nowhere. So here's the next example, B. It says sketch this f of x, 3 minus 2x, still a linear function, okay, and also sketch the square root of it, so y equals f of x, using a table of values. So to start off the table of values for you, we just have x, then we always just include the original function, 3 minus 2x, and then the square root of that function, y equals the square root of f of x. You can see it's not that hard once you get the original function and its values. I'm going to let you choose some values of x, work through it. Okay, it's linear. Choose about 4 values, then take the square root and sketch both of them on a graph. Okay? All right, so we told you here's some values that work. Jake figured them out. He said negative 11, negative 3, 1. He said it's kind of drafty in here, but what are the values that come along with this, Jake?
25, 9, 1.
25, 9, 1, which gives us points that are negative 11, 25, and negative 3, 9, and also 1, 1, which Zach pointed out. He says, you know what, 1, 1 looks like it's going to somewhere eventually be an invariant point, because now when we take the roots, we just take the root of this function. It's the y values. So this one becomes negative 11, 5, negative 3, 3, and then 1, 1, which is an invariant point. So whenever a y value is 1, it's invariant. Is there anything else that would be invariant as a y value from a normal function and the square root of its function? 0. So if the y value is 0, because the square root of 0 is also 0, that would be invariant. Or if the y value is 1, it's also going to be invariant. What we're going to do on this guy, we're just going to graph them in our calculators just so you get the habit of doing that, because on your diploma, you're probably going to be doing that as opposed to sketching them out. So in here, the first function was 3 minus 2x, and the second function would have been the square root of 3 minus 2x. Now there's two ways you could do it. You could hit the square root and go 3 minus 2x. You can also now dump in this if you knew how to do it. So I take the square root of what I put in y1. Doesn't matter what you do. Okay? I'm going to go back to my normal window, zoom 6, 3 minus 2x, a negative slope. And you got this. Now, we could see that down here, this negative part, is it affecting the square root of the function? No, it can't be negative square root. So let's change our window to something that might give us a clearer view. What could we get rid of? All the negatives. I'm probably just going to keep 1 just so we know that that original function still goes down there. But I'm going to say up here, let's say maybe negative 1. Oh, no, I didn't want to do that one. Let's keep this as negative 10. Sorry, I'm talking about my y's. Let's change that to negative 1. This will zoom in a bit of the graph. So we see that original one and the radical one now forming. And if you got closer and closer here, what would we expect to be happening right in that spot? That little overlap. Someone tell me a window that I could change that so I could see that little bubble on the other side. I could zoom box, someone says. Someone else is giving me window settings. We got window settings? Anyone? Let's say negative 1 to what? Was 2 enough? And then for the y's, we definitely don't need to go to 10. Let's try 2 again and see what we see. There's that original guy. Here's this one coming. And you can see there is that little bit, and that's an important characteristic of this graph, and it always happens at the same point, so we're going to have to talk about that later. It always blips over top of there. So what I want you to do with this function, I want you to just draw a nice sketch of it in your notes. So you have it included. And you can see what's going on here. The negative parts of the original function are not available in the radical function because you can't take the square root of a negative. And you can see this guy had a negative slope. It was going up towards the left, which means my radical function is going in the same sort of direction. So sketch that guy, and then we're going to talk about some domain and ranges here. All right, let's get this function table down here. We're going to talk about what the original function's doing, and then what that actually translates into when we talk about the square root of the function. We're going to talk about specific intervals of the domain. Okay, and the specific intervals we're going to talk about first off is when the original function is less than 0. So I'm going to use the function notation, inequality notations, because this is how it'll appear to you. But in normal language, if I'm saying f of x is less than 0, that means we're talking about negative values. So when the y is negative on the original graph, when we square root it, what does that turn into on the square root graph? An undefined point. Okay, because we can't take the square root of a negative, this turns into undefined values. So whenever the graph, the original graph, is underneath the x-axis in the negative y area, that part of the graph won't exist when we take the square root of it. The next interval is when the original function actually equals 0. If the original function equals 0, what about the square root of that function? It also equals 0, and we have the invariant point. Okay? And the other thing that we should know is that the graphs intersect there if it's invariant. Okay? So the original graph and the square root function graph, they'll intersect where y is 0. Now the next little interval is when we're talking about this chunk. So we're bigger than 0, we're not equaling 0, because that was our second column. But we're less than 1, because there's a whole different interval at 1. What's happening at that point? Jake's saying something. That little blip over top of the line. And unfortunately, you can't see what he's doing right now. But to put it in words, we're going to say this is where that square root of the function is above the original function. So that means, pardon? Thanks. Okay, that means if we were looking at a graph, if this was the original guy, the square root one is doing this thing, that little blip above it, and then it continues on. So that's what's happening in that interval. Now at 1, if the original function's 1, it's also an invariant point, which would mean the graphs intersect. Running out of room. So intersect on the next line. What do you think my last interval is going to be when it's larger than 1? What happens when the original function's larger than 1? Where do we know this part should be? It continues indefinitely, but let's just talk about, and I'm just going to go back a page here to look at this graph. Oh, not that graph. I don't know where the graph went. We'll look at this one here that we drew in the last one. We have our intervals defined here. Okay, if it was negative, which is this chunk right here, the radical function didn't exist. As soon as it got to 0, so that point right here, we got an invariant point. Here's another invariant point. Here's that interval. This last column is actually talking about these two lines here. The original one's the one on top. The square root one is always below it. So f of x is below the original function f of x. Okay? So these are the little intervals that we'll have to know, and you'll have to just understand the characteristics of what's going on. We got two little chunks left here. The first chunk we're going to say, if we could get to a new page, find domain and range of, and we have two functions we're going to look at. The first guy, A, is saying y equals 2 minus 0.5x squared, and y equals the square root of 2 minus 0.5x squared. So we're going to talk about the domain and range of these. And we should have enough information in our heads to at least look at the first guy and figure it out. We know it's a quadratic. We know this quadratic's opening up which way? It's opening down. And the highest point on this quadratic is 2, because this right here is signaling that this was a vertical translation 2 up. So my domain is x is an element of real. I can have any value of x. My range, y is less than, but also equal to 2. And we can write it in that other notation as well if we wanted to. Okay, so if I was to sketch this graph, we're just saying we got something like this happening. With, this point here being 2. Now I want you to enter this into your calculator and see what the square root of this thing is going to look like. So here's the graph from our graphing calculator. The taller one here, that I'll draw, I guess, in green, this is the original function going up to 2. And we know that that square root function will never exist below the x-axis because we can't take the square root of that negative. So the square root function is actually this part. And it's going down, I guess. I'm kind of stuck there. What is the highest value that that square root function reaches? The square root of 2. So our range for this part here should be y is everything what? So it's greater than or equal to 0 because it will never go underneath there, but it's also going to be less than or equal to square root of 2. And we could have written it this way if you like this notation better. Both of them are the same. What's my domain going to be? Is it -1 to 1? I'm seeing a -1 there. -2 to 2. Okay, so it's going to include those as well, because if I put -2 in there, the function equals 0. So there's one way to write it, or we could also write it in that other notation if you like it better, and both will be presented to you. So the domain and range, you just got to look at your graphs and kind of work with them. So here's the next one. We got 2, we said. Come up with a sketch from your calculator if you need to. So y equals x squared plus 5. And y equals the square root of x squared plus 5. So just the square root of that function. Come up with the domain and range, provide a little sketch, and we'll look at it. So here's the two graphs, the top one being y equals x squared plus 5, which we should identify this being 5 units up because it's the mother, x squared, translated 5 units up with transformations, which means on the radical function, that's going to be the square root of 5. So we probably have a lot of information here to find our domain and range. I'm going to do the domain and range in the new way to do it. How are we going to write the domain for the original function here? XER or infinity to infinity, but never including it because you can't get there. And what's our range going to be? Okay, everything greater than 5. So 5 is my lower limit, infinity is my upper. Can't reach infinity, but I am right on 5. Life is good. Now if I look over here, this one's not that much difficult, or more difficult. What's my domain going to be? It's still XER, or from -infinity to infinity. Now my range becomes, yeah, including the square root of 5, all the way up to forever. There we go. Thanks. Okay. Last little thing I want you to do in your calculators is going to be one thing, because this is a different type of function. We've been looking at these. Now this one's going to take a different sort of look for you. I want you to graph this and just compare what's happening between the two graphs. One's going to be y equals x squared minus 5. And then obviously we're still going to be looking at y equals and then the root of x squared minus 5. Take a look at the graph. Take a look at all the things we sort of talked about and see if it makes sense in the context of what we're doing. Let's just do that. Oh, we left that part out for Cole. So now we know that the original one is the blue line. The two little antennas of this looking graph are going that way. Why would this make sense in our context? What's going on? So, yeah, the bottom part here can't exist. So when I take the square root of these things, it's undefined. But then all the positive stuff, this blue part's going up to the right. My radical follows the same piece, and there's still that little blip over top. This guy's going up to the left. The radical follows the same piece, but there's that little blip. And you could find your domain and range here, which will be a little different. Okay, our domain's going to have two sections from it. Everything less than that x value, and everything greater than this. So the domain would be written in two parts, and your range would just be greater than 0 in both cases. So that being said, small little assignment, page 86, 3, 5, AD, and 7. That's what we're working on right now. Tomorrow we're going to start solving radical equations, and that will be our next lesson.